Hello everyone. Today I'll be presenting the article SatGuard, Counseling Endless and Bursty packet losses in low satellite network for delay-sensitive web applications. This presentation introduced SatGuard, a solution designed to address performance issues in low satellite networks, particularly for applications that require low latency and stable communication. Here's the agenda for today's presentation. I'll start with an introduction to low satellite networks, followed by identify what the problem is. Next, I'll start an overview of SatGuard and explain its key mechanisms. Finally, I'll share the result that demonstrates SatGuard effectiveness. Let's get started. As this figure shows that uh, the architecture of the low satellite. Low satellite operate in a constellation working together to ensure continuous global coverage. Communication begins at the user terminal, you can see there, connecting to the nearest satellite via a user satellite link, organized into beams that cover specific regions. The first satellite that receives the signal is called ingress satellite. Due to low satellite constant movements, frequent handover occur in the ingress satellite changes. Data is relayed through inter-satellite link until it reaches a satellite connected to the ground station. Uh, the, the data is then sent via a ground station link to the terrestrial internet, ultimately reaching the web server. While this design achieves low latency communication, the frequent handovers and dynamic routing present stability challenges. Something SatGuard is designed to improve. So you can you know that today's the usage of real-time application increase, and it is important to evaluate this application on the low satellite and monitor their behavior on it. Uh, for these goals, the authors set up the special uh, testbed to evaluate real-time application on the low. The experiment setup involved developing two laptops in New York City, one using Starlink and the other using optimum network connection. They tested the web browsing and web RTC via Currento, evaluating metric such as page load time, delay, and FPC. To assess performance under diverse conditions, WebRTC were tested from the Paris, Beijing, and Davis. Uh, in this slide, we talk about the result of the previous experiment. A Starlink exhibits significantly highly and more variable communication delays compared to the optimum networks, with delay frequently ranging between 400 millisecond to 600 millisecond, while optimum remain stable at around 300 millisecond or lower. Additionally, Starlink FPS performance is inconsistent, showing frequent fluctuations, whereas Optimum maintain a stable FPS across all routes. You can see in this figure. This instability in delay and FPS highlight a Starlink challenge in providing a smooth data flow, which can degrade real-time application performance. In this article, the authors investigate the root cause of detail by examining issue at both the network layer and application layer. In this slide, highlights a key network layer issue in low satellite network. Despite having a low average packet loss rate, the network experiences a sudden packet loss surges between 3 to 15%, disturbing data flow. You can see in the blue one. Similarly, although average delay remained low, frequent delays surge create instability. The sender-based retransmission mechanism further contributes to performance issue by causing high delay tails, whereas packets arrive much later than expected. This combined factor result uh, in unpredictable performance and poor user experience. This slide highlighted the application layer issue, specifically jitter buffer delay. A Starlink consistently shows a higher jitter buffer delay value than optimal, often exceeding 200 milliseconds. This instability forces the receiver to expand its jitter buffer, introducing noticeable delay in media playback. In contrast, Optimum maintain a stable jitter buffer delay value before 100 milliseconds, ensuring a smoother performance. This increased buffering on a Starlink contributes to latency issues, which SatGuards aim to address. Uh, to address the performance issue in low satellite network, this article introduced SatGuard, which include three key mechanisms. First, buffer migration that prevent packet loss during satellite handovers. Second, per beam timeout to prevent packet loss detection by adapting timeout values for different satellite beams. Uh, Third, reordering buffer to ensure packets are delivered in the correct order, minimizing delay and improving stability. In the next slides, I'll explain each of these mechanisms in more details. One of the key mechanisms in SatGuard is buffer migration. Uh, Buffer migration designed to prevent packet loss during satellite handovers. In traditional low networks, when a satellite is about to disconnect, any buffer packets that haven't been delivered are often lost. This is illustrated in the top figure where packets in the transmission buffer fail to reach their destination after the handover. Uh, Resulting of this event that retransmission failure and data loss. To address this, SatGuard introduced buffer migration, uh, buffer migration, which works in two key steps. First, uh, before handover occur, uh, SatGuard identify the next satellite that will take over the connection and proactively transfer buffer packet to that satellite. This ensure that critical data is preserved during the handover and we didn't need to retransmit again. The second step is recovery after handover. Once the handover is complete, the incoming satellite can effectively resume retransmission by sending the preload packets. This process minimizes packet loss and prevent delay spikes. By proactively managing buffer data during the handover, buffer migration helps maintain stable performance and reduce the impact of frequent disconnection in low networks. Now, let me introduce the second key mechanism in SatGuard. It's the per beam timeout. In low network, satellites use multiple beams to serve different area, and each beam may experience different delay. This can cause packets sent at the same time to arrive at different moments. Traditional timeout mechanism often mistake this delay packet as lost, triggering unnecessary retransmission. To fix this, SatGuard per beam timeout dynamically adjusts timeout value for each beams. As shown as a diagram, each beams has its own adaptive threshold, preventing delay packets from being misidentified as lost. This improves network efficiency by reducing false packet loss and avoiding excessive retransmission. So we talk about another mechanism. Uh, SatGuard's reordering buffer addresses packet disorder issue by introducing a ground assistant buffer that operate at ground station for terminals. It adds a follow level sequence number to packet for order tracking. How the buffer wait for local retransmission to maintain correct order, then detects follow level sequence number, then discard duplication packets. By this mechanism, reduce packet disorder and improve stability and performance in the low networks. The evaluation use a container-based LSM simulator that mimic real low satellite network dynamics, with each node running as a Docker container supporting real TCP/IP traffic. This setup was deployed on two servers with Intel Zen, and they simulate a Starlink constellation with 15/18 satellite across 72 orbital planes using grid connectivity and a performance was compared with another works. Uh, uh, in this slide, you see that the sidecar shows significant improvement at the network layer by maintaining high throughput and reduced tail delay across all tested routes. The result highlights a SatGuard ability to provide stable data transmission and minimize extreme delay, ensuring better network performance in the network satellite network. And this slide showed that SatGuard consistently achieved the lowest communication delay across all tested routes, as highlighted in the red dash boxes, and you can see it. This demonstrated that SatGuard effectively reduced delay, improving WebRTC performance in the LEO networks. Okay, is my presentation, and if you have any question you can ask me in the Teams. Thanks.